Okay, so even though we've been drawing carbohydrates as linear molecules, it's a really easy way to look at the stereochemistry of the carbons. In reality, carbohydrates exist as cyclic hemiacetals. So cyclic hemiacetals. So that's why I had it on bingo, right? So they undergo an intramolecular reaction, so a reaction between functional groups within the same molecule. And that's going to be how that cyclic hemiacetal is formed. And I'm going to need every last bit of room to draw my molecule on here. So I'm going to start out with a sugar molecule, 6 carbons long, so that we can go through this reaction mechanism. 1, 2, 3, 4, 5, 6. Then I'll go through and put on all my hydrogens and hydroxyl groups. Just takes a second here. Okay, so in this reaction, we're going to get a nucleophilic attack from this hydroxyl group down here, all the way up on this delta positive carbonyl carbon. Now, you might be wondering, well, why isn't it the hydroxyl group right next to it? Or the hydroxyl group on carbon number 4. Well, you got to think, that makes a really strained ring, right? So part of this is governed by ring strain. So now we're going to draw the cyclic structure, the cyclic intermediate that you get from this, where we now have a bond. Let's number our carbons real quick. From the OH group on carbon number 5 to the carbon that's part of the carbonyl. So if we draw that, it looks something like this. I'm going to draw, let's draw in black so we don't get confused. I'm going to draw a line structure this time, just because it's easier with rings. So here is hydroxyl group number 5. So it's connected to carbon number 5. Here's carbon number 6. So I'll number these in a second. So, getting ahead of myself. Guess I don't need that extra bond yet. That's just a big bond. I don't mean it to be so big. Oops. You're probably wondering, why doesn't she start this over? Because it takes forever. Okay, there we go. So let's go ahead and number our carbons here again. So we know that this oxygen that's positively charged now, because it's basically shared its pair of electrons when it went to form the bond with carbon number 1 over here. So that we know was attached to carbon number 5, and we see up here the CH2OH, which was carbon 6, so this must be carbon 5. Then we can go through our chain. Clearly this is carbon number 1. That was where the hydroxyl group of carbon number 5, let me just make that better, attacked. So we know then that this OH group right here is this one, and we know that this negatively charged oxygen is the oxygen that was part of the carbonyl. Then we can also take a look at where these groups ended up and how you know where they are, which side of the ring, and you can see that when you draw your line structure of your sugar molecule, when you convert it to a hemiacetal, those groups end up on the opposite, all on the same side of the ring. Okay, so we're not quite done with our mechanism yet, though. We've got this negatively charged oxygen, we've got this positively charged oxygen, so it makes sense that we can now finish our mechanism by extracting a proton, which will give these electrons to that oxygen and get rid of that positive charge. So then we can draw the final structure of our hemiacetal, which ends up looking something like this. So put all those groups back on. Now, it turns out when you do the chemistry, when you actually do the nucleophilic attack, and you do that final proton extraction, you can get two different arrangements of the hydroxyl group that you're going to get when you abstract that proton. So you could get the hydroxyl group pointing up, or if I just draw that part of the molecule, you could get that hydroxyl group pointing down. And if you notice, what we've done here at this carbon, carbon number 1, which used to just be attached to 3 different things. It was part of a carbonyl, so it was attached to an oxygen, a hydrogen, and the rest of the molecule. Now it's attached to 4 different things, 4 different groups. It's attached to this hydrogen, it's attached to this hydroxyl group, it's attached to this oxygen, which goes on to the rest of the molecule, and it's attached to this grouping right over here. We now have a new chiral center in our molecule. So this carbon is called the anomeric carbon. It was the carbon that was part of the carbonyl. So because it's a chiral center, that means that during that chemistry, we could get 2 different isomers. So the anomeric carbon generates an alpha and a beta isomer. And the way you tell, or the way you identify them, is based on whether or not the OH group is on the same side of the ring as the C6 or on the opposite side of the ring as the C6. So in this case, OH and CH2OH are both pointing up. This is the beta anomer, whereas here the OH is pointing down. It's below the plane of the ring, whereas C6 is pointing up. So this is the alpha. They're on opposite sides. So this is the alpha anomer. So now we've got 2 different isomers formed during the creation of this cyclic hemiacetal. Now you can have interconversion of those 2 isomers between alpha and beta, and that process is called mutarotation. So you know that cyclic hemiacetals are not that stable, so they can be opening and reforming with new stereochemistry. So some other fun facts about these rings. You could get chemistry that results in 6 atoms in the ring. We call that a 6-membered ring. If you do that, you get a molecule called a pyranose. That is a pyranose ring, and you'll see that name in some of the names of the sugars we're going to be looking at. Or you could get a 5-atom ring. If that happens, that form is called the furanose form of the molecule. And again, these are governed by ring strain during the reaction chemistry. The other thing to note about the structure of these carbohydrates is that they're not planar. So oftentimes you'll see a structure drawn in the ring as a Haworth perspective. So it might look something like this. And then this part is sort of shown darker to demonstrate to you that it's kind of like cyclohexane, which you know can form a boat or a chair, right? So even though these atoms are all in a ring, you can still have partial rotations about the bonds. So even though they're in a ring, they're not necessarily all in the same plane. Unlike the case of benzene, which has the resonance structure and all its atoms in the same ring. That's not the case with molecules like cyclohexane, or in this case, sugar molecules. So this leads to a phenomenon like sugar pucker, where you get these partial rotations, and it can be really important in the structure of DNA and RNA and the recognition of sugar groups in those interactions of proteins with DNA and RNA.